Let's turn our attention to time measurement. We have a simple problem. We have a push button switch connected to a PIC24 input, and we want to measure the pulse width that is generated whenever we push and release the push button. So we'll push the push button, the input will go low, we'll release the push button, and the input will go high, and we want to measure this pulse width. One approach for measuring this pulse width would be to record the value of timer 2 on this falling edge, also record the value of timer 2 on this rising edge, and then compute the delta ticks between these two timer 2 values and convert that delta ticks into a time. That would give us this pulse width. Assuming that we have timer 2 values recorded for these two edges, the computation of the delta ticks between these two edges is easy if the period register is at its maximum value. In that case, we simply take the rising edge tick value and subtract from that the falling edge tick value. This works only if this total pulse width is less than the period of the timer, which is 2 to the 16th ticks. And it will work even if the timer rolls over between these two values. This delta ticks computation becomes a bit more complicated if the period register is not equal to its maximum value. Let's use this diagram on this slide to try to understand this. There'll be two cases. One is if the timer 2 rising value is greater than the timer 2 falling edge value and no timer rollover occurred. That's going to be this case right here. Here's the rising edge capture value B. Here's the falling edge capture edge value A. B is greater than A and no timer rollover occurred. In that case, we're simply trying to compute this delta. So all we do is we subtract the falling edge value here from the rising edge value. So we're going to say this B value minus A value, and that will give us our pulse width in ticks. This assumes that no timer rollover occurred. If timer rollover occurs, then we have to use this equation right here, which is going to be split into two parts. The first part is going to be the time from the first falling edge until the timer edge rollover. This delta here is going to be PR2 plus 1 minus the timer 2 falling edge. So that's this portion right here. The second portion of this equation is simply going to be this delta time from 0, at which point the timer was reset back to 0 during rollover, to the second capture, which occurred on the rising edge, which is the B. That's this portion here. So this equation will give the pulse width in timer ticks. It must be noted that both of these cases here assume that the total pulse width is less than the period of the timer, which is less than PR2 plus 1 ticks. Note that this equation here, for the case of PR2 being its maximum value of 0x quad f, if we do this in 16-bit arithmetic and add 1, this is simply going to be 0, and this equation right here is going to simplify to the equation we used back here for the case of PR2 is equal to its maximum value of quad f. So now that we have an approach for measuring this pulse width, how do we write PIC24 code to make this happen? Let's first look at a straightforward implementation of this pulse width measurement. So what we're going to do first is we're going to configure our timer 2 for a maximum period register value of quad f. This means that we'll be able to compute the pulse width by simply taking the falling edge and subtracting it from the rising edge. We're also going to set our prescale value to 256. This is the maximum prescale value. What this means is that for a clock frequency of 40 megahertz, we'll be able to measure pulse widths up to about 420 milliseconds. This also means that one tick will equal to approximately 6.4 microseconds. So our main code is going to consist of the following. First, we're going to have a while loop that's going to loop in here as long as the button is released. When the switch is pressed, we're going to exit this while loop, and then we're going to record the timer 2 value in this 16-bit value called start. Then as long as the switch is pressed, we're going to loop in here. When it's released, we're then going to compute our delta ticks by taking our start tick value and subtracting it from our current timer 2 value. At that point, this delta variable will contain the pulse width in timer ticks. We're then going to convert those timer ticks to microseconds via this library function call, and we'll store that in this pulse width variable, and then we'll print that information to the screen. This inset shows the program running. With this example, we use an external crystal to generate the clock for the PIC24. We did that for timing accuracy. If you care anything about accuracy in your time measurements, you will not use the internal RC oscillator, as that can be off by as much as 5% and will also vary with temperature. This result here shows the button being pressed and released and the resulting pulse width measurements. So how accurate are these numbers being printed out by our pulse width measurement program? There are some inherent inaccuracies of what we've done here. The first inaccuracy comes from the fact that the timer 2 value is not recorded immediately when the switch is pressed. We're in this loop somewhere, and there's going to be some instructions executed to get to this point of where we're actually recording the timer 2 value. Another larger source of inaccuracy could come from the fact that there may be interrupt service routines executing in the background, and if there's an interrupt service routine that is executed between the time the switch is detected as pressed and the time that we record the timer 2, if there's an ISR executed during that time, then there could be an indeterminate number of clock cycles executed by the ISR, and our pulse width could be very inaccurate. What we really need is a better way, a more accurate way of measuring this pulse width, and it turns out that there is a better way to do this, which we'll discuss starting on the next slide. There is a hardware module in the PIC24 called the input capture module, whose specific purpose is to be used in time measurement applications. What its job is to capture either the timer 2 or timer 3 values whenever an edge, either rising or falling, and that's programmable, occurs on an input capture pin. This timer 2 or timer 3 value, when it's captured, is placed into a 4-element FIFO called the input capture buffer, and we can read that under program control. There's also a flag that is set for an interrupt service routine whenever an input capture event occurs. The advantage of using the input capture module is that this timer 2 or timer 3 module is captured by the hardware instead of trying to record it under program control as we were doing here. So whenever a particular edge that we're looking for occurs, then that timer value will be immediately transferred with no delay into this input capture buffer. Let's look at a use of this input capture module to solve the problem that we just solved in terms of measuring the pulse width of a push button. We're going to assume that this pulse width does not exceed the timer period. So in this case, we're going to first of all configure our input capture module. The IC1 input, the input capture input, needs to be mapped to a reconfigurable pin, so we're going to map it to RP13. We're then going to configure the input capture to use timer 2 as the base timer source, and we're going to want to capture on every edge. And we're going to want to interrupt on every edge as well. We're going to enable our input capture interrupt by setting priority greater than 0 and setting the interrupt capture interrupt enable bit to a 1. We're also going to configure our timer 2. In this case, we configured our timer 2 with the maximum prescale 256 to give us our longest possible period. We set our PR2 value equal to the maximum value as well. That way we can just subtract the two capture values, rising and falling, and get our delta ticks. The input capture interrupt is going to be caused every time a capture is made, and the capture is going to be made every time we get an edge either falling or rising at our pin. So we're going to use a little simple two-state machine in here. The initial state is going to be where we're waiting for the falling edge. If we come into here, then we've had the falling edge. When we enter the interrupt, we're first of all going to read the input capture buffer. We're going to save it in a local variable, and then if we're in this state here, we're going to save this current capture to a variable called last capture and advance our state to the next state. So the next time we come into here, we're going to be at the rising edge. So we're here. We're going to again read the input capture buffer, save it in here. We'll come into this state, and our pulse width in ticks is simply going to be the current capture minus our last capture. At that point, we're going to set a semaphore variable called capture flag to a 1. This will tell our main code, our foreground task, that we've made a pulse width calculation here in terms of ticks, and it's now ready for it to be consumed. And then we'll set our state here back to wait for falling edge. Our main is fairly simple. We'll do config basic, config switch 1, which is going to be RB13 for the pulse width measurement. Configure input capture module. Also configure timer 2. At this point, we'll output a message that says press the switch button. We'll wait for our semaphore capture flag to be set by the interrupt service team. Once that happens, we know that we have this variable here is going to be the pulse width in ticks. So we're going to convert this to microseconds and print that out to the screen, and then clear our capture flag variable. Here we have a PIC24 program with our NCAP measure simple.c program. It's using an external crystal oscillator for accuracy. We've pressed the button and we've measured a pulse width of 102,803 microseconds. We have a logic analyzer connected up to the same push button, and we see this pulse width here, and our logic analyzer has measured a time interval from our trigger to our rising edge of 102.8 milliseconds, which agrees with the value that was printed out of our program of 102,803 microseconds. What if you're trying to measure an interval that is longer than what one 16-bit timer can handle? You have a couple of choices. One is you can use a 32-bit timer by combining timer 2 and timer 3 into one timer. This is easy from a coding perspective, but it's expensive in terms of CPU resources. You can see the book example that does this. Chapter 12, timer 32-bit, switch pulse measure.c. Another way to do it is simply to track timer overflows for a 16-bit timer and include this in the equation. This results in more complex code, but only uses a single 16-bit timer. You can see the book example that does this, Chapter 12, NCAP switch pulse measure.c. This diagram shows how timers 2 and 3 are combined to a single 32-bit timer. Timer 3 is going to be the most significant word. Timer 2 is going to be the least significant word. The period register will be the concatenation of PR3 and PR2. To configure this for a 32-bit timer, you have to write bits in the timer 2 configuration register, and the special bit T32 in this register must be set to a 1. For detecting rollover, the timer 3 interrupt flag is used for that purpose. For more details on how the 32-bit mode works, please see the book example on this topic. If you want to use only one 16-bit timer to measure intervals that are longer than one 16-bit timer, then you have to track timer overflows. This equation shows how timer overflows are included in the delta ticks computation. You track the timer 2 overflows in the interrupt service theme for the particular timer that you're using. In our example, we use timer 2. This function here in the library, compute delta ticks long, implements this equation by you passing it the start capture time, the end capture time, the timer period register value, and the number of overflows that occurred. This particular function is used in the example that illustrates how to measure a long pulse width using one 16-bit timer and code that tracks timer overflows. Our previous time measurement examples measured the pulse width from falling edge to rising edge of a single pulse. But what if you have a repeating square wave of a fixed frequency and you wanted to measure the period? Then we need to measure either rising to rising or falling to falling edges. For more accuracy, when you do this measurement, you should use the input capture modes that captures these edges either every 4 edges or every 16 edges. This is included because this reduces the error by a factor of 4 and a factor of 16 respectively. See the book example, Chapter 10, NCAP freq measure.c for more information on this mode. Another common time measurement example in the microcontroller world is real-time clock calendar keeping. For example, you'd like to keep track of seconds, minutes, hours, weeks, days, and months. And while you can do this in software, it's much better if you have hardware support for this. And it turns out that on some PIC24 microcontrollers, they have a real-time clock calendar module that simplifies keeping this information. All you have to do is add on the secondary oscillator crystal that is this particular frequency, 32.768 kilohertz. You may recognize that number as being 2 to the 15th. This means that a 16-bit counter would wrap around every 2 seconds, or a 15-bit counter would wrap around every second. This particular oscillator frequency is critical in real-time clock calendar keeping. For more information on how to use this particular module, you can see chapter 10 RTCC.C.